Welcome to lecture series on digital electronics under EPG Pathshala. This module is dedicated to understand some advanced design concepts. So far we have discussed several combinational circuits as well as sequential circuits. We have seen how Boolean algebra can be applied in designing several applications. Now it is the turn to understand a specialized topic which is related with control unit design. Let us first try to understand the importance of control unit in the overall digital system course. When we talk about a microprocessor, basically there are two separate sections. One is a processing unit and the second one is a control unit. Whenever we talk about control unit, the role of control unit is to control, coordinate, communicate and synchronize variety of operations which are related with the microprocessor. The same concept can be used for any control applications in the industry. Now, whenever we talk about the control unit design, we think about implementing certain control strategies with the help of either hardware or hardware plus software logic. Now, when we talk about the control unit design, there are two aspects which are normally preferred. The first aspect is related with hardware approach and the second one is a microprogrammed approach. In a hardwired approach, we think about designing the control strategy with the help of one flip-flop per state method. Whereas, there is a second method that is adopted under hardwired approach, that is the sequence register decoder method. The second method or the approach that we prefer is a microprogrammed approach. The hardwired approach has several disadvantages. To overcome them, we prefer a microprogrammed approach. A microprogram is written either in PLA or PAL and then it could be executed. So, we prefer a programmable array logic and a ROM based approach. So, these two are having certain advantages. Smaller modifications in the control strategy requires modification in certain programs and that could be easily implemented using the microprogrammed approach. Now, in this module, we will focus it on all these four different methods of designing the control unit. Let us explore the world of control unit design. Let us get familiar with the learning objectives. Let us begin with understanding the role of control unit. Second, to get familiar with different types of control unit. The features of hardwired control unit will be determined next, and finally, the architecture of microprogrammed control unit will be explored. The CPU can be viewed as integration of two parts, data path and a control unit. The typical organization of modern von Neumann processor is illustrated here. Note that the CPU is connected to input devices, output devices and memory. The CPU reads information sent by input devices. It further processes the information based on the instruction obtained from the memory and sends the information back to output devices. It is important to note that the arrow just indicates the direction of data flow. Actually, these devices are connected by address, data and control buses. It is worthwhile to further discuss the CPU in details. The processor or CPU is an active part of computer which does all the work of data manipulation and decision making. The data path unit is the hardware that performs all the required operations, for example, registers, ALU, shifters, multiplexers, decoders and interconnecting buses. The data path includes the ALU, registers including program counter, memories and multiplexers used in processing elements of the processor. All these operations of data path perform various operations depending upon the instruction encountered. The coordination among these components is the task of the control unit. Some components of data path may feed certain signals back as a status signals to the control unit, using which some conditional instructions might be executed. Design of data path is related with processor organization. A good data path is the one through which data signal takes minimum end-to-end path for execution, giving highest possible speed. The control unit is the hardware that tells the data path unit what to do in terms of activating or enabling the internal section, selecting the desired operation, movement of data between various parts, etc. It basically includes basic combinational and sequential circuits to perform following different functions: timing, control, coordinate, communicate and synchronize. Control unit performs the major functionality in the processor and is perhaps the most complex part of any processor. The control unit is also referred to as a decode unit since it decodes the instruction. The instruction fetched from the memory and stored in the instruction register is fed to the control unit and appropriate control signals are generated by it to execute that instruction. These control signals are fed to various parts of data path as their control signals. For example, ALU needs the ALU function code, multiplexer requires select lines, etc. The control unit, which is almost biggest part of processor, has to be designed carefully to get best performance. The ALU is called the heart of the processor and the control unit is viewed as the brain of the processor, that is the brain within the brain. The control unit performs following tasks: generates timing signal for operations, controls the flow of data through the data path unit, coordinates the activities of other units within it and synchronizes the operation of internal blocks. In addition to the basic functions, the control unit performs three major tasks in context with instruction processing. These are fetch, decode and execute. The control unit generates these signals for proper operation of fetch unit, decode unit and execute unit. For the basic processor, these operations are performed sequentially, that is, first fetch the instruction with the help of fetch unit and keep it in the instruction register. Second, decode unit is instructed to decode the instruction stored in the instruction register. And third, next it begins with execution of the instruction with the help of execution unit. In many advanced processors, these tasks can be performed concurrently with the help of pipelined or parallel processing units. Let us take an overview of functions of control unit in a processor. First, it directs entire computer to execute a stored program instructions. It also communicates with both ALU and memory. Further, control unit instructs ALU that which arithmetic or logical operations is to be performed. It also coordinates the activities of all blocks of computer. In traditional control unit designs, the control sequence needs to be identified. Once a control sequence has been identified, the sequential circuit for implementation of control unit must be designed. As the control unit is a sequential circuit, it can be designed by following traditional sequential circuit design procedures. There are several disadvantages of traditional sequential circuit design procedures for control unit. In many cases, due to large number of states, this method is impractical. Second, traditional design methods based on state table and excitation tables are difficult to manage and complicated. Third, control circuits based on this method require large number of flip-flops and gates, indicating use of only SSIs. Fourth, the number of connections based on SSI circuit are more. Hence, this method is inefficient for design implementations. Fifth, If the number of circuits are reduced, then design becomes irregular and difficult to analyze later. Last, troubleshooting is also difficult. Looking at the disadvantages of traditional design, a new approach based on combination of sequential logic design and register transform method is preferred. This leads to two types of control units: hardwired control unit and microprogrammed control unit. The name hardwired control unit originates from the fact that the basic control signal generator of the control unit is hardwired. It means that control signals required for the instruction execution are generated by a specially designed hardware logic circuits. Usually SSI and MSI circuits are used for implementation. Various circuits are formed and interconnected by wires to generate a control circuit. There are two approaches for implementation of hardwired control unit. First, one flip-flop per state method, and second, sequence register decoder method. Once the connections of these logic circuits are made, then we cannot modify the logic design. If any modification or changes are required, then the circuit must be rewired to fulfill the requirements. Let us now discuss the one flip-flop per state method. For the implementation of control logic, this method utilizes one flip-flop per state method. In this technique, only one flip-flop is set at a time and other flip-flops are reset. A single bit is made to propagate from one flip-flop to another under the control of the decision logic. In such an array, each flip-flop represents a state and is activated only when the control bit is transferred to it. In this method, for 4 states there is a need of 4 flip-flops, and for 16 states there is a need of 16 flip-flops. This indicates this method requires large number of flip-flops. If we consider traditional sequential circuit, it requires 2 flip-flops to generate 4 states and 4 flip-flops for 16 possible states. This indicates this hardware logic requires maximum number of flip-flops. This definitely increases the cost of implementation. The main advantage of this method is its simplicity in design. This type of control logic can be designed by inspection of state diagram, which describes the control sequence. It also saves lot of design efforts, increases simplicity and reduces number of combinational circuits required as compared to traditional design approach. Figure indicates control logic with one flip-flop per state method. It basically contains two major sections. First, it has a decision logic and number of D flip-flops. The number of D flip-flops in this circuit are 4. All these D flip-flops receives the data input from the decision logic. These flip-flops generates the output in the form of a state Ti, where I varies from 0, 1, 2 and 3 in this case. These outputs are also fed back to the decision logic, indicating the present state of the system. The decision logic accepts external input conditions if any, and also produces signals for other control outputs. At any given instant of time, only one flip-flop is equal to 1 and all other flip-flops are equal to 0. The transition from present state and the next state is a function of present Ti, that is a 1, and certain external input conditions. The next state is generated when the previous flip-flops are cleared and a new one is set. Each of the flip-flop outputs are connected to the data processing unit to initiate the micro operation. If there is no need of external inputs, then the circuit reduces to a straightforward shift register with a single bit shifted from one position to the next. If the control sequence is repeated again and again, then the control sequencer is reduced to a simple ring counter. A ring counter is a type of shift register with the output of the last flip-flop connected to the input of the first flip-flop. In a ring counter, the single bit is shifted continuously from one position to the next position in a circular manner. This is why one flip-flop per state method is also known as ring counter controller. Let us now talk about sequence register decoder method for hardwired controller. This method of implementation utilizes a register to sequence the control states. The register is decoded to provide one output for each state. For a sequence register with n flip-flops, the circuit will have 2n states. The decoder accepts n input and generates 2n outputs. Let us consider a sequence register with 4 flip-flops, indicating there are 16 states. The decoder with a capacity 4 by 16 will be used to generate 16 outputs corresponding to 16 different states with one output per state. This method of implementation uses MSI circuit for both sequence register and decoder. Figure indicates the implementation of 4-state control unit designed using sequence register and decoder technique. There are 3 major blocks in this system. These are decision logic, sequence register and decoder. The decision logic has 2 inputs, namely external input conditions and present state inputs to generate the inputs to sequence register and other control outputs. The output of the decoder is used as the present state for decision logic. The sequence register has 2 flip-flops and decoder will decode the outputs of these flip-flops. Decoder accepts 2 inputs and generates 4 different outputs for each state in the register. The next state in the sequence register is a function of present state and the external input conditions. As the outputs of the decoder are available, it is convenient to use them as present state variables rather than use of direct flip-flop outputs. The other control output is also the function of present state and external input condition. This other control output may initiate micro operations in addition to the decoder outputs. In many cases, the external inputs are not required. Then the sequence register reduces to a counter that continuously sequences through 4 states. This is why such method is also referred to as counter decoder method or a ring counter method. Let us discuss microprogrammed control unit. The basic difference between these unit structures and the structures built using hardwired control unit is the presence of the control store, that is microprogrammed memory. This memory is used for storing the words containing the encoded control signals necessary for instruction execution. In microprogrammed control unit, subsequent instruction words are fetched into the instruction register by usual technique. However, the operation code of each instruction, if not directly decoded but contains the initial address of microprogram contained in the control memory. The instruction opcode from the instruction register is sent to the control store address register. Based on this address, the first micro instruction of microprogram that interprets execution of this instruction is read to the micro instruction register. The micro instruction contains its operation part encoded control signals, usually as several bit fields. The fields are decoded in a set of micro instructions fields decoder. Besides the encode control signal fields, the micro instruction contains the address of next micro instruction of the given instruction microprogram and a control field used to control the activities of micro instruction address generator. The last mentioned field determines the addressing mode or the operation to be applied to the address embedded in the current micro instruction. The last micro instruction in the microprogram of a given instruction is the micro instruction that fetches the next instruction from the main memory to the instruction register. There are two approaches for the implementation, namely PLA control, that is programmable logical array control, and ROM based, that is microprogram control logic based on read only memory. The PLA or ROM based approach uses an LSI circuit such as PLA or ROM. Any modifications or changes can easily be implemented without changing the wiring. This is the main advantage of these techniques. Let us begin with PLA based method. A programmable logic array PLA is a kind of programmable logic device used for implementation of complex combinational circuits. PLA has set of programmable AND gate planes which links to a set of programmable OR gate planes. As compared to PAL, PLA has both AND and OR planes programmable. The PLA control is basically similar to sequence register and decoder method, except that only all combinational circuits are implemented with PLA, including decoder and decision logic. By using PLA for combinational circuits, it is possible to reduce the number of ICs and number of interconnecting wires. Figure indicates the architecture of PLA based control unit. It consists of only two sequences, the first sequence register and second PLA device. The sequence register sets the present state of the control unit. The PLA has external input conditions as well. The PLA outputs are dependent on present state of the sequence register and external input conditions. The PLA outputs decides which micro operation should be initiated. The PLA outputs are also fed back to the sequence register to decide the next state. In advanced PLA, the device includes not only combinational blocks, but also some flip-flops within the unit. Such PLA provide single chip solution for control unit design. Finally, now let us discuss the ROM based method for designing the control unit. The main function of control unit is to initiate series of sequential steps of micro operations. At any given time, the certain operations can be initiated and all other remain idle. The control variable at any instant of time can be represented by a strings of ones and zeros, which is referred to as control word. The control word can be programmed to activate various components in the system. A control unit whose control variables are stored in a memory in an organized manner is called microprogrammed control unit. Each control unit stores the control word. Each control word of the memory is known as micro instruction. The sequence of micro instructions is referred to as microprogram. As it is very rare to change the microprogram, hence ROM is usually preferred as the memory. The microprogram requires the control words must be put into the ROM to generate micro instructions. One can perform the read operations to fetch the micro instruction. The content of word in a ROM at a given address specifies micro operations for the unit. Figure illustrates the architecture of microprogrammed control unit. The organization consists of three major sections: the next address decoder, control address register and control memory, which is usually a ROM. ROM basically contains all control information required for the controller. The control address register specifies the address of control word in the control memory. In this configuration, the ROM is treated as the combinational circuit capable of accepting address value as the input and generates control word as the output. The contents of control word remains on the output wire as long as the address value remains in the address register. The control memory generates the output indicating a micro instructions. The micro instruction specifies one or more micro operations for the components of the system. Once these operations are complete, then the control unit must determine the next address. The location of the next micro instruction may be the next one in the sequence or may be located somewhere else in the control memory. Some of the bits of the present micro instructions are used to control the generation of the address for the next micro instruction. This indicates that the output of next address generator is a function of external input conditions as well as next address information obtained from control ROM. Hardwired and microprogrammed methods have advantages and disadvantages when performance and cost are compared. Let us start with speed. Hardwired approach is fast because control signals are generated by combinational circuit. The best approach when the speed of operation is most important. The performance is high. Delay in generation of control signals depends upon the number of gates, and last, bugs in the hardware design cannot be fixed in the field. Next parameter is ease of prototyping. Microprogramming can be used for rapid prototyping of new designs or emulating several instruction sets. Hardwired design is complex if large. Let us now consider the flexibility of use. Microprogramming provides considerable flexibility in implementing instruction sets and facilitates adding new instructions to existing machines. Let us now summarize the key points regarding the control unit design. Whenever we talk about any design strategy, the first thing that we need to identify the problem specifications. Based on that, we identify what are the things those need to be implemented. The traditional design process requires implementation of the control strategy with the help of either SSI or MSI, and that is true in hardwired approach. Now, whenever we talk about implementing any control strategy using either one flip-flop per state method or sequence register decoder method, it is observed that any small modification in the system requires wiring the whole hardware or modifying the whole hardware. These disadvantages are basically used for overcoming certain problems, like whenever we talk about designing anything at very high speed or simplicity in the design, that requires a hardwired approach. Let us look at the two methods that we have studied specifically, which employs some kind of a microprogram or micro instructions. In a microprogrammed approach, we assume that the control strategy is written in the form of certain microprogram, and these micro instructions are stored in the memory either by using programmable approach, PAL approach, or we can go for ROM based approach. In both the cases, the program or micro instruction is stored in the memory. The first advantage that is very clear, that if there are any alterations or modifications those are required, that requires simply changing some of the memory locations or modifying the program, and that you can do in site programming or in situ programming. You do not have to take it into laboratory. You can have field programming that is possible. That is why we can use either PAL, PLA or FPGAs or CPLDs depending upon the design complexity. This module was focused to understand the control strategy that could be implemented using hardwired approach or microprogrammed approach. Thank you.